Alright, welcome back everybody. In this we're going to look at the last example on the Introduction to Optimization lesson. We have a rectangle. A rectangle is to be inscribed under the curve y equals -1/8 x squared plus 8, so that two of the vertices on the rectangle are on this curve and the other two lie on the x-axis. What is the largest area this rectangle can have, and what dimensions give that area? So first I'm going to draw a quick little sketch of what's going on here. We've got a parabola that opens down, and we're inscribing a rectangle underneath this. Parabola. And we want to find the area of this rectangle. Okay, so the hardest thing for me probably in this problem is coming up for the expression that represents the area of this rectangle. We'll realize that we've got multiple different rectangles that we could inscribe underneath here. You know, we could have a rectangle that looks like this, or the original green one that I represented. But whatever the case may be, this distance right here is going to be the x-coordinate of the point where the rectangle intersects the parabola. And the y-coordinate of that point, since the function is y equals -1/8 x squared plus 8, the y-coordinate is going to be -1/8 x squared plus 8. And that means that my area of my rectangle is going to be the height, -1/8 x squared plus 8, times the width, and since x is the distance from the origin to one side, the entire width is double that. And so now we have our expression for the area of this rectangle in terms of x. It's -1/4 x cubed plus 16x. And now we're going to optimize. Now, let's realize, before we optimize, let's talk about our constraints on the width of the rectangle. First of all, for the domain of the rectangle, x has to be bigger than 0. If it's not bigger than 0, then it's not going to form a rectangle. And it has to be smaller than whatever the x-coordinate of this point is. And the x-coordinate of that point is 8. So our critical value is going to be somewhere between 0 and 8. Alright, now let's optimize. A prime is equal to -3/4 x squared plus 16. We set that equal to 0. And we're going to go ahead and solve it for x. For once, I'm not going to solve this by graphing since it's a quadratic. We end up with x squared is equal to 64/3, and so x is equal to plus or minus the square root of 64/3. Only one of those values is going to be important, the positive one, and now I'm going to go ahead and find that value. The square root of 64/3 is 4.619. So x equals 4.619. Alright, so now I need the dimensions of this rectangle, and I need the largest area that the rectangle can have. So the area here is going to be, I'm going to store that value so I can use it. Store that value into what, A. Alright, so then I want -1/8 a squared plus 8 times 2a. I didn't want to type all those digits, but I did want to use all those digits. I didn't want to type them, but I wanted to use them. And so we get that the area is 49.267 Now there's no units given in our problem as far as inches, centimeters, whatever, so we're going to leave our units bald. The area is going to be 49.267, and the dimensions are 2 times x, 9.238 by, and negative 1/8 a squared plus 8, 5.3 repeating. So there are the dimensions of our rectangle and the area that answer this problem. The dimensions of largest area. You know what, I forgot to do something important in here that I really should have done. I haven't verified that that's the maximum. It could be a minimum. So let me go back to my sign chart for my derivative, 4.619. Let's see, when x is 1, the derivative is positive, and when x is 6, the derivative is negative. So that is indeed a maximum, and so that's what we want. Our maximum area is 49.267, and our dimensions are as written there. All right, that's the end of example 3. See you guys next time. Have a great rest of your day.